Hey everyone, and welcome to today's Explainer. Today, we're stepping right into the shoes of lead designers for a real-world Grade 8 geometry engineering mission, the Solid Geometry Design Challenge. If you've ever wondered how engineers figure out exactly how much material goes into the containers we use every single day, or how much those containers can actually hold, well, you're in the right place. We're going to break down the math step by step using some really clear visual models to guide us. So get your calculators ready because we are putting our spatial reasoning to the ultimate test today. Quick look at our roadmap for today. We'll start with the design challenge task, move into your geometry toolkit, build the container model, and then test your design assumptions. Finally, we'll go over the evaluation rubric and wrap things up with a recap and a transfer question. Let's get right into it. All right, Section 1, the design challenge task. Let's dive right into your primary objective as chief engineers. Okay, so here are the raw constraints for our container design. Our task is to mathematically model a cylindrical drum. The exact dimensions we're pulling straight from our OpenStock source material are a radius of 2.7 feet and a height of 4 feet. Now, take a look at the assumptions listed right below that. In the real world, obviously, a steel drum has thick walls and it gets dented or has ridges, but to make this mathematical model work, we have to follow mathematical practice standard number 6, which is attending to precision. We have to explicitly state our assumptions up front. So, assumption 1, the container walls have negligible thickness. That just means our inside volume calculations and outside surface area calculations use the exact same radius. And assumption 2, we're treating this as a perfect mathematical cylinder. Being precise about these assumptions right from the jump is really what separates good math from great engineering. Moving on to Section 2, your geometry toolkit. Let's see how all this builds into the mathematical models we're going to need to execute the design. To actually build this container, we need to completely understand two distinct fundamental concepts, volume and surface area. Think of volume as the 3D space inside the container. Like if you were filling this drum with water or oil, you're talking about volume. And because it's three-dimensional, we always measure it in cubic units, so in this case, cubic feet. Surface area on the flip side is all about the outside of the container. It's the amount of sheet metal you'd need to manufacture the drum, or even the amount of paint you'd need to coat the outside. It's a two-dimensional covering, so it's measured in square units, like square feet. Honestly, mixing up square and cubic units is probably the #1 mistake engineers make, so let's make sure we keep this distinction locked in our minds. To really physically visualize what volume is, we use what's called the unit cube. According to the core math standards, volume is measured by finding the total number of same-size units required to fill a space without any gaps or overlaps. A unit cube is literally just a cube that is 1 unit long, 1 unit wide, and 1 unit high. So when we calculate that our drum holds a certain number of cubic feet, I want you to picture packing that drum completely full of 1 foot by 1 foot by 1 foot solid blocks. It gives us a really solid physical understanding of what that math actually represents in the real world. And this framework brilliantly illustrates how to think like a mathematician. Notice mathematical practice number 3, construct viable arguments and critique the reasoning of others. And hey, there's practice 6 again, attend to precision. In this challenge, just punching the right numbers into your calculator isn't enough. We have to be precise with our units, and we have to be able to construct a logical argument for why our design works. These practices are totally non-negotiable for our mission today. So how exactly do we apply those practices? Well, we use a super streamlined, step-by-step problem-solving strategy adapted straight from the OpenStack's pre-algebra text. First, you read and identify the goal. Second, name the variables, like using an R for radius. Third, translate the situation into a geometry formula. Fourth, solve it using algebra. Fifth, check to see if the number actually makes logical sense. And sixth, and this is absolutely critical for communication, answer with a full sentence and proper units. This framework empowers us to tackle really complex spatial problems systematically. All right, Section 3, building the container model. We have our constraints and we have our toolkit. Let's get to work on the blueprint phase. And it's time for our first pause check. The formula for the volume of a cylinder is V equals pi times the radius squared times the height. Our radius is 2.7 feet and our height is 4 feet. For this, I want you to approximate pi with 3.14. So please pause this explainer right now, grab your calculator, plug in those variables, and calculate the exact volume of this drum. Test out that spatial reasoning and hit play when you're ready. All right, welcome back. If you followed our 6-step strategy, your answer should be exactly 91.5624 cubic feet. Let's walk through the immediate reasoning real quick. Following the order of operations, you've got to square the radius first. So 2.7 squared is 7.29. Then you multiply that by the height of 4, which gives you 29.16. Finally, multiply that by our approximation of pi, 3.14, and that yields 91.5624. But notice the unit we are heavily emphasizing here: cubic feet. A raw number is totally meaningless without the unit. We basically just proved that we can perfectly pack exactly 91 and a little over a half of those 1-foot unit cubes into our drum. Great work! Section 4, testing your design assumptions. Now, what's really interesting about this phase is that it forces us to shift our thinking from the empty space inside the drum to the physical material needed to build the outside of it. Which brings us to pause check 2. We're putting our design through a material stress test. The formula for the total surface area of a cylinder is S equals 2 times pi times radius squared plus 2 times pi times radius times height. The first part covers the flat top and bottom circles, and the second part, the 2 pi RH, covers the curved side. So here's the challenge for you. If a client comes in and asks us to double the height of this drum, how exactly does that affect the amount of material needed for just that curved side? Go ahead, pause the explainer, construct a mental argument, and then come back when you've got it. Okay, let's break down the algebraic reasoning here. Doubling the height directly doubles the area of the curved side. Why? Well, if you substitute 2h into the formula instead of just h, the expression becomes 2 times pi times r times 2h. Using the commutative property of multiplication, you can literally pull that 2 all the way out to the front, showing it is exactly twice the original 2 pi rh. Now, why does this matter? Because constructing a simple algebraic argument like this lets us predict real-world manufacturing costs instantly. If our material supplier says the curved side is the most expensive part to build, we now know for a fact that doubling the drum's capacity by doubling its height will exactly double that specific material cost. That is the power of mathematical modeling. Section 5, the evaluation rubric. We've built the model, we've tested the constraints. Now let's look at how our final engineering designs are actually evaluated in a professional setting. So the crucial point is really captured in this compact evaluation rubric. Notice that the raw math is only 1/3 of the grade. The first column is accuracy, and this maps straight to Math Practice 6. Are calculations correct and are our square and cubic units perfectly specified? The second column is reasoning, mapping to Math Practice 3. Did we construct viable arguments like we literally just did with the height change, rather than just guessing? And finally, communication. Are our findings stated in complete, clear sentences so the client actually understands us? Because in geometry and in engineering, the clarity of your communication matters just as much as the accuracy of your calculator. And finally, Section 6, recap and transfer question. We've successfully navigated the core mission, so let's debrief and lock in what we learned today. Here's your rapid-fire recap of what we've mastered in this explainer. The task. We learned to treat geometry as a true design challenge with explicit constraints and assumptions. The models. We successfully applied the formulas for cylinder volume and surface area to map a real-world object. The precision. We know the absolute necessity of distinguishing between square units for surface material and cubic units for interior space. And the strategy. We used a structured 6-step method to not just solve the math, but to verify and communicate it like absolute professionals. Before we wrap up, I have one final puzzle for you. Imagine our client changes the design constraint entirely. Out of nowhere, they now want a spherical container. The formula for the volume of a sphere is V equals 4/3 times pi times the radius cubed. So how would you mathematically prove whether a sphere with a 1.5-foot radius holds more or less volume than the 91.56 cubic foot drum we designed today? I challenge you to apply our 6-step strategy to this new formula, run the numbers, and construct a viable argument. Thanks so much for joining me on this mathematical design mission today. Keep questioning the world around you, and I'll catch you in the next explainer.